Welcome back to the 6th lecture on Riemann integration. And in the last lecture, I left an exercise for you to investigate. Okay, I didn't want you to come with a complete proof or anything. Okay, the result I wanted was we proved when alpha x equal to x, the identity integrator, and if f is a function on the interval a b, which is continuous except at finitely many points, we proved it is Riemann integrable, where alpha x equal to x, that is alpha integrable, but alpha x equal to x, we call it Riemann integrable. So we had already done that. Okay, and then we proved if f is continuous on the entire interval a b and alpha is any arbitrary increasing integrator, then f is alpha integrable. Then the natural question arose whether I can prove somewhat more general result. What is the result? That is, f is continuous on AB except at finitely many points, and alpha is an increasing integrator, arbitrary. Can I still prove f is alpha integrable? This was a question which I posed and asked you to investigate. Okay. And if you had gone through the earlier proofs, okay, there are three results. You remember, with respect to Heaviside function, we proved that if f is integrable, alpha integrable, you'll find only if alpha f is continuous at C. And next we proved if f is an increasing function and alpha is an arbitrary increasing integrator, then f is alpha integrable if we assume alpha is continuous. Yeah, right. Third, we proved that if f is continuous except at finitely many points, the integrator is the identity integrator, then f is integrable, Riemann integrable. If you have gone these three proofs carefully, there is a very natural guess. Almost all of you could have got it. I do not know how many got it, because in the class I can watch your face and identify. Okay, but it's impossible here. But I'm sure most of you would have done that. Yes. What did you guess? So let f be continuous except at finitely many points, and assume alpha is continuous on the entire interval, then f is alpha integrable. This much you should have got it. Okay, I would really like to hear from you, those who think I don't want you whether you got a proof or not. You understand that? What I want you is whether you can imagine such a result, whether you can arrive such a result. See, mathematics is always done like that. Most of the time, you guess whether it could be true, then you try to arrive at a proof later. I just wondered, that's the way you create mathematics. I just wanted to see how many of you did that. I will, at least about a few of you have done that, I will be really happy. Okay, if you have got that much, okay, this formulation, please say, yes sir, I got it. Okay, that will be very nice. You should be proud of yourself. Very good. But actually, if you go through this to proof, you can prove slightly more general result. That's what I'm going to indicate today, but not with complete proofs, because as I said, these three results, the Heaviside function and f continuous except finitely many points, then f is monotone but alpha continuous, these three results, right? You should go through again. If you go through it, I'm going to indicate a proof of the most general theorem. What is the theorem? F is continuous except at finitely many points. Now alpha is an increasing integrator, but alpha is continuous at points of discontinuity of f. That's all I need. I don't need alpha to be continuous everywhere. Are you following? Then I want to prove alpha is integrable. You get it? Before I share my screen, think about it. Have you got this? This is okay. Without writing, I'm going to say pause, review and proceed, PRP, right? And please remember, if you got some kind of an idea about this formulation, you should say this in the comment. Yes sir, I got it. I'll be very happy. Okay, now unfortunately 30 minutes of lecture I had given without sharing, so this is the second recording. Okay, so let us go back. This is the theorem I want to prove. F from AB to R is bounded and continuous except at finitely many points T1 to TR. Let alpha from AB to R be increasing and also assume alpha is continuous not on all of AB, it's continuous at these points of discontinuity T1 to T. That's enough. Then I want to say all okay, F is integrable, alpha integrable. This is a theorem. The proof is, as I said, combination of these three proofs. What is the proof? The Heaviside function thing, and this is the identity integrator and continuity finitely many points. Then if alpha is F is monotone and alpha is increasing and continuous, then F is alpha integrable. So the combination of these three proofs will give the result what we want. Okay. Again, as usual, inside it, I'll go back and do that. So what we want to do, you are going to give me an epsilon positive. Then what do I have to do? I have to find a partition P so that U of P alpha minus L of P alpha is less than epsilon. Okay. This is all I have to do. Right? Now I'll try to mimic the proof of identity integrator, the proof of this fellow. Okay. This is a proof I want to and use the results. So what do I do there? So what I did was those points at T1 to T, and here the thing is this is going to be something like this: mk mi minus small mi into delta alpha I. Right? Now I want to choose a partition, okay, of alpha A, alpha B, so that my alpha Ti are enclosed in very small, because you understand this, at the point Ti I cannot control mi minus mi because the function may not be continuous, and at other points I know how to control, you understand. So I'm going to concentrate only those I. So what I do is these things I put in a small thing. So let us say this is put in the interval alpha Ti minus 1 by k, alpha Ti plus 1 by k. Okay, k is very large, so that all of them are contained in the interval alpha A to alpha B, and when I is not equal to j, the interval alpha Ti minus 1 by k, alpha Ti plus 1 by k, and alpha Tj minus 1 by k, alpha Tj plus 1 by k, they are all pairwise disjoint. Okay, these things are all disjoint, that's all I mean. Okay, if I choose k large enough, I could do that. Very good. Okay, now the next thing is, and this I have to put a crude estimate for these intervals. What is the crude estimate I have to do? That will be, let us say, as usual, mod fx is equal to c, then this will be 2c into delta alpha I, where delta alpha I is going to be this minus this, that, right? Are you following? That is going to be 2 by k. And how many such intervals are there? R interval, therefore it is 4cr, I hope I wrote it right, into, this is the contribution of all these things. This I want it to be less than, let us say, epsilon by 2, therefore I can choose k. So that is happened. Once I have done that k, so fixed that k, then what will I do? Let's look at the complement of these intervals. I'm just looking at only this. Okay, although there are two complement of this interval. On these intervals, my function f is uniformly continuous. Therefore, I can choose a partition of this interval so that u of p minus l of p alpha here will be less than something, let us say eta, but there are going to be r plus 1 such intervals. So r plus 1 such intervals, and in each of the interval I want it to be less than eta. But you understand that? What is that beta? That is u of p, that p is not this p, p only corresponding. Okay, u of p or alpha minus l of p is less than, what do I want? Some eta. You follow that? And there are r plus 1, therefore the sum of all those good things should be r plus 1 times eta, that should be less than epsilon. This eta is not to be confused with that eta, therefore eta should be less than epsilon by 2, right? So I got a partition. So I got a partition for this, and this is the partition for this, and I got a partition for this, this is a partition for this, and so on. So I find a final partition P of the interval. Okay, these things will correspond. Okay, right. So here I will have a corresponding interval A to here. This will be a point Pi minus 1. Okay, please go through it. I am very vague here. Okay, but I am sure that all of you will be able to go through the argument. But if you don't want this kind of technical result, assume alpha is continuous on the entire interval, then you will get a simpler proof. Okay? So please try. If you don't get it, please write in the comment. I will produce a video just for about 20 minutes for this completely. I will explain. Okay, let's check whether I'm recording tablet. Now I am ready to prove what I wanted to do yesterday. I want to discuss Riemann's approach. Integration. This is either Riemann integration, so-called Riemann integration, or Riemann-Stieltjes integration. This highly genius approach with a physical intuition, and in fact physicists and engineers will love this approach. Okay, see, let us go to that. Suppose I'll just start with only Riemann integral for a positive function. Suppose this is the one. Okay, suppose I know I can find the area. Okay, this is integrable. Okay, don't worry about when I want to talk about integration. This cannot be the first point, right? I cannot say assume integral, but just as we are already done, let's assume it, right? Okay, so I want approximate area. So I want to approximate. What do you think I will do? Okay, I take a sample. I take some sample points. Okay, and subdivided this thing into this kind of intervals, and in these intervals I take a partition, okay, of this interval AB, and take some samples. What are the samples? Samples are this. Something, it could be anything. Now this is your F. Okay, call this as T1, T2, Tn, where that is Ti belong to the interval xi minus 1 to xi. Okay, this is sample. Then this area, if it is very sufficiently close, I expect this area should be this times this. For example, my sample this would have taken this as a sample, and this may be my xi minus 1 to xi. Then I will take this, the original. Okay, this I took more, here it was less, but somehow this, I think this is a good approximation. Are you following? Let me make it clear. So suppose P is a partition, right, and let T be T1 to Tn, where Ti is some arbitrary point in the interval xi minus 1. I call them as tags. Ti is the ith tag. Ith tag. T. Right. Therefore, I want to define what is called Riemann sums. Riemann sum is, let me call as Riemann sum of F with respect to the partition P, with respect to the tags T, summation f of ti to delta xi. I could understand this, and here thing, this is my tag, then the area, so this for the getting here, the following. So this is called Riemann sum of f respect to the partition T and the set of tags T. But remember, if you change the tags, this SPT, S of FPT will keep changing. This depends on the tag also. It does not depend only on the function of the partition. It also depends on the tags. Okay. So this essentially you are simply taking a sample. Understand? You subdivide it in something. Again, it is good to have physical intuition. Okay, suppose I have a metallic plate, okay, and with a variable density. I want the weight of this metallic plate. How will I do that? And break it into small pieces. Okay, small partition. Okay, and take an arbitrary sample point. Look at its density. Look at the area of this thing. Multiply area times this density, and here area times this density, area times this density, and area of this times density, and add up. It will be very good approximation the weight of the thing. That's of course intuitively okay. There are a lot of ifs and buts, but that's what Riemann thought of. You understood this? Are you sure? Now suppose I gave an alpha and an integrator. Okay, now let alpha be any function from a, b to r, not necessarily monotone, of course bounded. Okay, then how do you think I will define S, F, P and T alpha, and T is again a set of tags corresponding to the partition, some set of tags for the partition. How do you think I should define? Go back. How will I define? I will define it as f of ti into delta alpha I. Yes, so this is f of I to delta alpha. Yes, have you understood this? This is called the Riemann sum of f corresponding to the partition P and a chosen set of tags T with respect to alpha. The important thing here is at present I am not assuming alpha to be increasing. In that case delta alpha will be non-negative always. Here I do not know. It could be of 9. Okay, I am just, are you following? That's very crucial. Now I want to say this is Riemann's definition. Okay, I say f is alpha integrable on AB. What is alpha? Alpha is any bounded function. If there exists a real number a, that there exists a partition P, that for every partition Q is finer than P, and for every set of tags in Q, what should happen is look at S, F, P, or S, F, Q, T, alpha minus A should be there is a partition P, so that for every epsilon positive the partition P, I mean, do not get someone psyched by this. Think of convergence of numbers. How will you do that? When I want to say the sequence xn is convergent, what do I want to say? Then there is a real number x, so that for every epsilon positive you want to say there is a natural number n, so that for every natural number k greater than or equal to n, xn minus x is modulus less than. Something very similar. In place of there is a capital N natural number, I am saying there is a partition P, and what is that? then in place of for every k greater than equal to n, I am saying for every partition q which is finer than p. Okay, now this Riemann sums depend upon that tag, therefore I don't care what tags you take in q. You understand that? For the same q there is infinitely many choices of tags, so I don't care whatever tags you take, s of q t alpha minus a must be. Okay, just pause, review and understand the definition. Okay, don't get psyched, get used to this, and it's not as difficult as it sounds. Okay, think of this, we took essentially a sample, that's all we did. Now what I want to say what is the weight of this metallic plate. Says that, okay, it has a weight a if now you take any partition. Now what you do, you have some partition p fixed, after that take any refinement of the partition, and each of the refinement partitioning piece areas you take any arbitrary samples and add them. Okay, you get an approximate weight, that approximate weight will be epsilon close to. Okay? And go through this kind of definition 2 or 3 times. Do not try to learn by heart, that's what many students go through. The you will begin to appreciate, it will become very natural. Think in terms of the physical intuition, you will never ever forget. So now there are two things. See, our earlier definition, you should call this the Darbous approach to Riemann integration or alpha integrability. Is alpha integrable. What are that? It said that for each thing you have UP alpha and LFP alpha, and then you did something with this. Okay, whereas Riemann's approach is through so-called Riemann sum. Okay, in terms of tags. Now before even we prove any theorem or something, suppose I say, let us assume, okay, let me even say that, okay, the theorem we want to prove is let f from AB to R be bounded, okay, and alpha from AB to R be bounded and increasing. Then f is alpha integrable with respect to Darboux via Darboux approach. If only if f is integrable via, you understand this theorem? Okay, remember for Riemann approach I don't require any condition on alpha except it's a bounded function. But for Darboux approach, so far I needed alpha to be an increasing bounded function, right? So I have a function f, so it may be alpha integral with respect to Darboux definition. Then I want to know whether it is going to be integrable with respect to Riemann definition. Yes, yes. Okay, because when I say it's a integral with respect to Darboux definition, alpha is already increased. Understand that? Therefore, when the integrator alpha is increasing, Riemann approach and Darboux approach yield the same set of integral functions. The function f is alpha integrable with via Darboux approach if it is alpha integral via Riemann approach. That's not enough. What do you want? Okay, both are integrable, but they may yield different integrals. You understand that? The integral with respect to Darboux approach may be different from the integral with respect to Riemann approach. Yeah, I forgot to say, if okay, if such a f is alpha integrable, if such an a exists, we call a to be the alpha integral of f. Again, there is another problem. I have to say that such a is unique. What do I mean by that? If f is alpha integral with a and f is alpha integral with b, okay, then a equal to b. That is uniqueness of the, it is, the proof is similar to the uniqueness of the limit of the sequence. Okay, are you following what I'm saying? Otherwise I cannot say a the alpha integral of f. Okay, b may also have the same property. Yes, please understand, right? So the uniqueness actually will follow from this also. How does it follow? Suppose f is, assume the result of this theorem. Okay, f is alpha integrable with respect to Riemann, okay, via Riemann approach. So let a be one such. There may be b also, I don't care, but I am going to say this a, then I am going to say f is alpha integral via Darboux approach, and integral a is going to be integral alpha. Notice that this is already defined, so I am going to say a equal to b. Therefore, if f is alpha integral with r with b as a b, then that b is also equal to integral f d alpha. Therefore, a equal to b. You understand the logic? Pause. Begin to think. Don't worry about mathematics. It will be automatic. You can create your own mathematics. You will be able to analyze and think ahead. Okay? Are you happy? Next, even before launching the theorem, I want, whenever I see a theorem, I don't immediately launch into a proof as textbooks do or teachers do. I tried to understand the theorem. It's like, having a good dish which you like very much, then you don't immediately swallow. You put it in your mouth, and okay, and then you enjoy it. Okay, you take a lot of time, and then only you swallow it. You understand? Don't immediately be the same way. Anyway, right? Now, what is the advantage of Riemann's approach? As I said, physicists and engineers love this definition. And not only that, as you might have seen, differentiation is easy, integration is, okay, given a function, I may not be able to find the integral of the, suppose I know it's integrable. Now, and most often in scientific calculation, engineering purpose, the exact value of the integral may not be needed. What I need is a very good approximation. Now let's look at Riemann's thing gives a very good approximation. If I want to find the weight of this metallic plate, okay, so what I have to do, if I know this as integrable, then what all I have to do is take the domain interval and make it very large, very fine partition, and take some sample points, then form this thing, summation f of ti into delta xi or delta alpha I. Okay, that will be epsilon close to your a, right? Because if the partition is very fine, then it should be a very good approximation. You understand this? Are you following? The same thing, if you want, I think mathematics is fun if you really understand what is happening rather than just in the theorem proof. Let us say, suppose I have a and a sequence of rational numbers which converge to square root 2. You know how to do that, right? Something like a plus 2 by a or some such thing. I forgot 2 by a, right? Some such thing. If you look at, okay, an plus 1 equal to an by 2 plus an, then I think an converges to know this. And these are all rational numbers. Suppose I start the original thing to be 1 or 2 or something, all these things will be rational numbers. So what is the advantage of this? It says that if n is very large, then an is a rational number which is as good as root 2. It is very close to root 2. Therefore, for all practical purpose, I can use this number wherever root 2 was needed. Follow that? Sequence I would explain this. Nothing. Please pause, review. Now we want to give a proof of this theorem. that we will stop the lecture. Okay, I will prove this equivalence of these two statements. So let f be alpha integrable via Riemann sums. Okay, with a as alpha integrable. Okay, it may not be unique, but we are going to say that a has to be something else. So I want to prove f is alpha integrable via Darbous approach. What does that mean? First I have to say it's integrable. Next I have to say what is the integral also. There are two aspects to the theorem. This means I have to look at u of p alpha minus fp alpha then epsilon, where epsilon is sufficiently close. Given epsilon positive, there is a partition p, so that for all partitions q which are finer than p, u of q alpha minus l of q alpha is less than epsilon. This is what I am supposed to prove. Yeah. Okay. Now let us go. So suppose you gave me as epsilon, okay, and f is alpha integrable in Riemann sense, right? With integral a, right? Therefore, what do I know? There exists a partition that for every partition finer than p, and for every set of tags modulus s f q t alpha a is less than epsilon or epsilon by 2. Not worry about it. Clear? This is our definition of Riemann integral. Go back. For every epsilon positive, there is a partition p. For every partition, tag this. Now this is where we are going to do something. Now let's look at the interval xi. Okay. Now for u of p alpha, what do I will have? I will have summation mi delta alpha. Understand? The p is the same or q is the same for any q. Right? Fix a q which is finer than p. Now for every set of tags this happens, right? Now what is mi? Mi is the LUB. Therefore what do I know about mi minus epsilon? That's not an upper bound. What does that mean? There is a ti, okay, in the interval xi minus. So with what property? F of ti must be greater than mi minus. You understand this? Yes, right. Now in place of epsilon, keep this epsilon. This is not the same epsilon, I'm sorry. Okay, therefore for each k, let us take k natural number. Okay, there exists a tki k, okay, depends on k which is greater than 1 by, right? There is a tki, so that f tki is greater than mi minus. You understand this? Depending upon k, I can fix. Follow that. Now what are these things? Let us write tk. This is tk1, tk2, tkn. This is a set of tags in q, right? Therefore what do I know? I know yes. What is s f? Therefore what is s f t q and tk going to be, okay, something f of, let me write it, f of ti to delta alpha I, and remember delta, now my alpha is increasing, therefore delta alpha I are non-negative. See, this is the place where we are going to use this, right? We are going to use inequality. What? But fti is greater than mi minus 1 by k. Are you following? Therefore this is greater than, each of these terms is greater than mi minus 1 by k to delta alpha I. That is summation mi delta alpha I minus 1 by k into delta alpha. Have you understood? Yeah? Okay. Right? This, you know what, this is delta b minus delta va. This is a finite quantity, I don't know what about. Therefore, as k, this sum as, okay, where does it converge to? It converges to summation by delta alpha I is u of p alpha. Have you understood this? Yeah, this is a finite thing, this is a bounded thing. Actually alpha b minus alpha a by 1 upon k. Therefore, as k tends to goes to 0, so goes to this, right? Therefore, modulus of u of p alpha minus a is going to be limit of s of q by p pk, and I'm sorry, this minus, right? This minus a goes to this minus a, right? Modulus is less than epsilon, but as limit goes to this, remember modulus is a continuous function. You remember that xk converges to a, then xk minus a in modulus goes to 0, right? Therefore, this will be, each of them is less than epsilon. Therefore, this, yeah. So what have we done? So we have shown that u of p alpha minus a in modulus now equal to f. Similarly, you can prove L of p alpha minus a now equal to f. Sorry, not p. Keep forgetting. Okay, I hope all of you understand this. Okay, what I said that. Okay, I'll be more worried about thinking. So some of the symbols may be wrong. I may write 2 times 3 equal to 5, but it's 2 times 6, not 2 plus 3, like that. Anyway, is this okay? Now, therefore, what is u of p alpha minus L of p alpha? That will be less than or equal to epsilon. But there is no modulus needed. Okay, therefore, f is alpha integrable. What sense? Sense of Darboux. You understood this? And next, what do I know? This says, let's look at this. So this says that, so a minus epsilon is now equal to L of alpha, L of q alpha, right? But that's less than equal to L of q, L of alpha, but that is less than equal to L of q of alpha, but that is less than equal to q of q alpha, but that's less than equal to a plus epsilon. Follow that? Therefore, what do I get? So I see that u of alpha is L of alpha and u of alpha are lying between a minus epsilon to a plus epsilon. And for which epsilon? For every epsilon. Understand this? How m of alpha, sorry, L of alpha and u. But remember, they are supposed to be the, okay. So they lie between a minus epsilon to a plus for every epsilon. That means u of alpha but this is curl of f. Please pause. Proof is actually easy. If my own notation was slightly confusing, go through. Okay. Now what is that I have to do? I have to prove the converse. What is the converse? Let us assume f is alpha integrable Darbous. I want to know whether it's alpha integrable, right? Okay. So if I want to prove its f is alpha integrable Riemann sum, I should get out of a, right? That's very important. But since we have the theorem already says this a must be, since f is alpha integral in Darboux sense, this a I take as integral f d alpha, which is the Riemann is just Darboux integral. You understood that? This is my choice. Therefore, what is that I have to do? I have to say, if f is alpha integral Riemann sense, what I have to do? You give an epsilon positive, I have to find a partition p, so that for every partition q and p, and for every set of tags, the s of f q t alpha minus integral f d alpha. This is my a. Have you understood this? Okay. Right? This is all I have to prove. Now, since f is alpha interval in Darboux sense, since you gave me an epsilon, I know there is a partition p. F is alpha integral Darboux sense. For this epsilon, this is given. For this, there is a partition p, so that for every partition q minus than p, what do I know? Q of p alpha minus alpha. Then this is a Darboux integrability, right? Okay, good. Now let's look at what happens to s or q, sorry, for every, see, I keep writing the same thing, yeah. Okay, now let t be any set of tags. Then let's look at s f q t. This is something like of ti delta alpha I. Remember, delta alpha i's are again all non-negative. See that? That's where I needed, for this theorem I need alpha to be increasing function. Now where does fti sit in between mi and capital M? Therefore, where does this sits here? Yes, f q t alpha is than or equal to q f and greater than or equal to, yes. Are you happy with this? Okay. Now what is that I wanted to estimate? I wanted to estimate, right? But remember, L C Q of P alpha, L of P alpha, then epsilon. Follow that? Therefore, what do I get? Q of P alpha is less than L of P alpha plus. So what do I get from this? Do I get the result? Okay, what am I supposed to show? So I have to prove something to integral. Let A integral f d alpha, this is the Darboux Riemann just Darboux integral. Then I have to say this minus a. So I have to start with A here. Yes. So this tells me I have to have a slightly different that. Now you can see I am thinking. So this I will abandon. Not going to work. Okay. So instead I am going to do slightly different way. Because you can see upper interval, lower interval should come. So I have to do that. So I'm sorry for this, but let us, no problem. Let's look at upper interval f alpha. You gave me an epsilon positive, right? To prove alpha integrable in the Riemann sense, you gave me epsilon positive, right? So for that epsilon, I know there is a partition. See, this is the, you see that this is u of alpha is what? GLB of u f p alpha for every partition, right? Therefore, if I take u of alpha plus epsilon, okay, what do I know? I know this is not the lower bound for this set. Therefore, there is a partition 1 that u of 1 alpha, then u of alpha plus epsilon. You understand this? And similarly, there exists a partition P2 that is greater than LF alpha minus epsilon, because this is the least upper bound. Therefore, anything less than that is not an upper bound. Therefore, there is an element. So, if P equal to P1 union 2, then these results still remain P1, P2 replaced by P. Are you following? Because u of P alpha will be then this, and therefore less than or equal to this. Therefore, similarly, L of P alpha will be greater than or equal to this. Therefore, L of P alpha will be greater than. Understand? Therefore, this remains true for this thing. Just 1 second. Yeah, you understood this? Now let Q be any partition which is finer than P. Let T be any tags in Q. Then I can repeat the proof. Okay. Let us look at yes, F, Q, P, alpha. This, as we did, is equation FTI to delta alpha I. The persistent thing. Yeah. Now remember, FTI lies between Mi and capital Mi, and delta alpha is greater than or equal to 0. Therefore, I can squeeze. Therefore, what do I have? Yes, F Q T alpha is less than or equal to upper sum F P alpha and less than or equal to lower sum L F P alpha. Are you convinced? Very good. But this fellow I know is U F. What do I know? U of P alpha is less than U of alpha plus epsilon, and this fellow is greater than LF alpha minus epsilon. Am I right? Just make sure. Yeah. Yeah. So what I have found? I have found that yes, F Q T alpha is less than or equal to U of alpha plus epsilon. But remember, my F is alpha interval in the Darbous sum. Therefore, the lower integral F LF alpha and upper integral LF alpha are the same. Therefore, it's same as A, and this same as A minus epsilon. Yeah, where A is common value. Therefore, what I have shown, for any partition Q and for any set of tags T, where this partition Q defines P, I have proved yes, F Q T alpha minus A is less than epsilon for every Q which is finer than P, and for every tags in Q. We approved it. What does that show? It shows that F is alpha integrable in the Riemann sense, and the integral in the Riemann sense is same as the integral in the Darbous sense. The theorem clear? I'm sorry for the goofing, but as you know, it's all learning process. So you can also see I don't try to memorize anything and come back. Okay, I hope it's a little tortuous for you possibly, but go through it. You will see that I don't keep some things in memory and prepare well for the lecture and then try to do that. I try to think I can prove it. I try to do that, and I saw towards the end it didn't work, so I changed the trick. Okay, this is how you learn it. Most often what you do is we teachers know what we are going to lecture. We sit at home, prepare very well, sit in the faculty room, prepare very well, and then give it. Okay, so you think that I already know the proof. Yes, I know the proof because I worked through. But you very rarely we think the proof in the class in front of you, in front of the students. I am trying to do because that's the way you can. I hope you appreciated that. Okay, right? And deliberately you can see I'm trying to be vague and more vague because this is the way I usually do in the classroom also. First few lectures I'm extremely crystal clear. I take a lot of pains to explain everything. Okay, and as time goes by, okay, I try to go like this because the students should get trained so that they can have the confidence. Yes, I know how I can sit down and work out the details, write a textbook proof. Okay, I'm sure all of you can do it, right? Try it again. Okay, we'll stop the lecture. Thank you very much. We'll meet again in the next lecture. What we will do, we will use these two definitions are equivalent if alpha is integrable, right? So now we will look at the class of alpha integrable function and prove various properties like linear, it's a vector space, and it's going to be something like monotonicity result and the so-called basic estimates for integral, because most of the time integrals cannot be evaluated, but what you need is some kind of a good estimate. So we will look at all these things. Okay, we will enjoy. Okay, sure. Okay, I'm stop recording. We will meet again.